problem, and the statement of the problem is to predict the distances between floating stack of magnets for any number of magnets. So I have a diagram here, pretty much the magnets are in alternating orientation, meaning this is north, south, south, north, and so on and so forth. And when they're stacked upon each other, they float in equilibrium. And essentially, we denoted the distance between magnet 0 and magnet 1 for any number of magnets as d1, between 1 and 2 is d2, and so on and so forth. And since these magnets are in static equilibrium, because they are at rest, then we can produce Newton's second law equations for the net force on each of these magnets and set these net forces equal to 0. Alright, so for one floater, for example, there's two forces being exerted on magnet 1. One is the repulsive force from magnet 0 on magnet 1, and then the gravity force. And since this is at rest, then the net force is equal to 0. And this is the same for 2 floaters, 3 floaters, 4 floaters, and so on and so forth. However, something important that I want to point out is that as you add 3 and more floaters, there is still an effect on magnet 4, for example, on magnet 3 that is repulsive. However, when you add magnet 4, there is also an attractive force between magnet 4 and magnet 2, and then a repulsive force between magnet 4 and magnet 1. And that's important because that changes the net forces on each of these magnets and must be noted in the formulas here. Okay, so these are some of our basic assumptions, like the magnets are equal width, height, mass, and whatnot. Okay, so the first approach pretty much was to calculate magnetic force as a function of distance. So this is a 3-step process. First, we measure the B field or magnetic field of one magnet. Then, using that data, we calculate the magnetic moment of the magnet, and the magnetic moment is essentially the strength of the magnet. And then, using these two values, we calculate force of the magnet. Okay, so this is our B field data that we collected using a magnetic field sensor as we moved the magnet a certain distance away from the sensor. And from this data, we were able to create a fit, like a best fit model, using this equation and calculate the magnetic moment to be around 1.4 in value. Okay, so now with these two values for both magnetic field and magnetic moment, we're able to calculate magnetic force. So there are two models for calculating magnetic forces in relations with magnets. One is when you're at far distances, you treat a magnet as a dipole. And however, as you decrease the distance between magnets, you can no longer treat the magnet as a dipole because the separation of the poles is no longer negligible. So this equation comes into effect. And these equations are both known and have been proven in literature. And the main difference between these equations, besides the setup, is that this is force as a relation of distance to the fourth, and this is force as a relation of distance to the second. Okay. So now we have two models for measuring magnetic force, and we need to verify which one is more accurate. So essentially what we did was we calculated the force by distance for the far magnets using, for example, this is the permeability of free space. This is the magnetic moment we previously calculated, and then we have this data here, and this is force by distance for that. And this is our experimental force and the theoretical force. So this is the theoretical force values, and our experimental force is the actual force by data we measured using the process I'll explain later. So as you can see, in comparison to the theoretical force is quite similar to the experimental force as we increase distance. So this model is potentially acceptable. So then we did the same thing for close distances, in which we plugged in these values. This is the same value. This is the volume of the magnet we're using. This is the magnetation, which is pretty much the strength of the magnet again. Okay, so we did the same thing for this, and we got force by distance data, and we plotted it against the experimental and theoretical, and we found that this line also fits pretty well. So we can say that these models are fairly accurate, but we can't determine which model is more accurate in determining the force between magnets. So what we did was we pretty much simplified our approach, and we turned it into a very basic equation in which force is related to c, which is a constant over distance to some power, and c would be the values that are found here that are the properties of the magnet, such as magnetic force and whatnot. And then d to some power would be the relationship between force and distance. So pretty much we want to solve for c in order to be able to like solve the Newton's second law equation that we previously described. So we tried powers of 2, 3, and 4 because that's what we, because the other equations that we previously mentioned use 2 and 4 as relationship, and we just decided to use 3 because that is also a potential power that we raise distance by. Right, so we took force, in order to solve for C, we did force times distance, and so we took force distance data using this model, using this experimental setup. So what we did was essentially, this is a force sensor, and it senses this force as equal to gravity when there's no magnet here. And as you move this magnet closer, these magnets are attractive, so as you move this magnet closer in distance to this magnet, the force on this magnet, the downward force on this magnet increases. So we're able to generate a graph for how force varies by distance as you move these two magnets closer to each other, and these are error bars. Alright, so using this data, we plugged into MATLAB, and essentially we analyzed and created 3 separate fit models for this data. One for when p equals 2, one for when p equals 3, one for when p equals 4. And we took the error of these fit models into consideration. So we noted that the error for when p equals 2 was quite low, about 1 to the 10 to the negative 4th. And similar for when p equals 3, but p equals 4 was about twice this error. So we decided to continue our experiments with only p equals 2 and p equals 3 as a potential model. So then we calculate the c values using this graph here and using the previous simplified equation here. So now, at this point, we have all the information that we can use to solve this Newton's second law equation. And so pretty much what we did is we wanted to solve for the distances between magnets, because that is the problem statement and that is the crux of the problem. So essentially we set this net force, which is the Newton's second law equation, equal to some error. And we created a theoretical array of distances and plugged in these values into these equations, and then generated an array of errors for all these array of distances. And so essentially what we want is that we want the 2 distances that we can arrive at that minimizes error and makes it closest to 0, because then the magnets will be modeling a Newton's second law equilibrium problem. So this is the equations for 2 magnets. So and then to measure the minimum error, use root mean squared error. Okay, so this is a graph of the error in a color plot. So essentially this is our distance 1 theoretical array of distances, and this is distance 2. And for example, you can see at this point, when distance 1 would be 7 centimeters, and then distance 2 would be very low. That doesn't really make sense because the magnet would be here, and then the first magnet would be here, and then the second magnet would be there, which in the problem doesn't really make a lot of sense because you would expect this to fall. Oh, okay. So pretty much what we did was we found the minimum error here, and we calculated the distance values, and then we returned the distance values that we believe that would be the distance values when you plug into the previous equation that would get you a net force closest to equilibrium. So we extended this approach for 3 magnets. This is the point right there for distance 1, distance 2, and this is a slice of distance 3. And we extend this to 4 magnets as well. And this is the slice that has the min error, and we have 3 values of distances that produce the min error. Yeah, so this is a measurement of our actual measured distance, which is 2.4 centimeters, and our predicted using this model distances. And as you can see, for both P2 and P3, as you can see, these values are fairly accurate, and that as you go on, you notice that as you add more magnets, you notice that the percent discrimination between the actual and for the model for power equals 3 becomes much greater than that of power equals 2. So from this, we decided pretty much that we thought the relationship of force as a function of distance is inverse squared. So we continue this approach for 4 floaters as well. Okay, and there's a lot of points of error within this equation, within this experimental setup. But I want to get to the conclusions. So we concluded that we explored 2 possible models of force as a function of distance using equations that are known and accepted. And we did this by measuring the force and calculating the magnetic moment of the magnets. And from this, we created a simplified model of force. After this, we created a simplified model of force as a function of distance, where force equals c over distance to some power. and we collected force by distance data and in order to calculate the values of C for about 3 kilo 0. Yeah. Okay. And then we. Okay.
That's all the time we have for the presentation. We have 2 minutes for clarifying questions from the opponent.